So what we want to look in a little bit more detail in is at the possibility that a change over time in the extent of volcanic activity, and in particular a increase in the frequency and the scale of volcanic eruptions, could have been a cause for the Little Ice Age. What you see in this diagram are three different parameters. The first is an interpretation of the effects of volcanic forcing based on the known volcanic episodes, volcanic activity that occurs over time. And you can see that in each case the effect is negative. It causes a reduction in the amount of total solar irradiance, but the effect is very short-lived. It's essentially a spike. Happens, collapses. Now, the second variable is shown down here, which is variation in the amount of solar irradiance due to solar activity. And there are two different models, variations shown in here. One is if you have strong variations over time, and the other if you have weaker variations over time. Now, all other forcings are shown down here, and you can see that with the exception of relatively recently, their impact is limited, and we're going to effectively just ignore those. I've added some arrows in blue and in orange here. What they represent in blue are times at which there is a reduction in the amount of solar irradiance, and you can see that the volcanic eruptions are always associated with that, and at times in orange in which there is an increase in the amount of solar irradiance. So here we have a situation where we have a negative effect on the solar irradiance as a result of the volcanic activity, but we actually have an increase due to solar activity. In this case here, you can see that the negative effects of a series of episodes of volcanic activity are compounded by the fact that it's a time at which we have a reduction in solar irradiance. What we're going to do is we're going to investigate the possibility that the Little Ice Age was triggered by volcanism, but then, given that the effects of single volcanic episodes are very short-lived, we're going to need some factor by which we then sustain that initial effect. Now, the data for this study by Miller and colleagues comes from a series of tundra vegetation that is now, as in between 2005 and 2010, exposed principally on Baffin Island here in the Canadian Arctic. So what they did was they collected a series of these mosses that were exposed, and they dated them. Now, the key thing is that all of these were in situ. They were entombed below the ice. They didn't show any movement because these small ice caps on top of these low relief landscapes essentially freeze to the surface, and there's very limited flow. So we can be confident that these were killed at the time they were entombed and have not been moved subsequently. So we essentially have in situ rooted tundra vegetation that was last alive at the time they were covered by that ice cap. So the carbon-14 date then marks when they were buried below the ice. Now, this is a complicated diagram, but you can see that there are 5 key elements picked out here. The first then is total solar irradiance. The second is sulfate aerosol loading. That's effectively the impact of volcanic activity. Here's the age of the moss samples kill dates. So in other words, the bulk of the samples recovered were killed at this interval of time and this interval of time, around 13 to 1500. There is data also from a sediment core that spans this interval in the ocean in the surrounding area. And again, what I'll point out here and come back to is that the varves are thinner here and then increase in thickness up here. and there's also data for how thick Arctic sea ice was over the period of time as well. So the first key thing then is, here's our series of data. The kill dates are clustered between about 1275 and 1300, between about 1300 and 1425, and then again a second big peak at 1430 to 1455. So collectively 1275 to 1455. So this marks a time at which the ice had to actually grow, entomb these living mosses, kill them, and then keep them concealed below ice until 2005 to 2010, when they re-emerged from below the ice. So that marks a major interval of ice growth, and then thereafter ice cover being sustained. Now the interesting thing is that these, particularly this peak and this peak, are coincident with large-scale episodes of sulfate loading into the atmosphere, which of course, as we've already seen, is a major signal and derived via volcanic eruptions. But remember, our big problem is that the effects of volcanic eruptions are themselves very, very short-lived. What we have here between the period of about 950 to 1250 AD is very, very little kill dates. So in other words, there was no expansion of the ice to incorporate and entomb living tundra vegetation. The ice was either static, therefore, neither advancing nor retreating, or it was actually in retreat. And of those two options, it's probable that the ice was actually in retreat, because the varve thickness is much reduced in the Arctic Ocean at this particular time. And of course, don't forget, from when we looked at the sedimentology of varves, these represent the seasonal melts, and of course you have to be proximal to the ice to carry the material out into the either lacustrine or ocean setting and deposit it, and then switch off that signal when you go back to the winter period and you freeze the system up again. So if you're not doing that, it suggests that there isn't actually ice in the area at that particular time. So it looks as if the ice was actually in retreat, and then all of a sudden advanced relatively rapidly in response to the volcanic eruption, but then was able to sustain itself afterwards, despite the fact that these volcanic eruptions would have had very, very short-term effects. So this is our problem. We can set up the model. The volcanism forces negative total solar irradiance. There's a depression there and a depression there, coincident with the two maxima for kill dates. So we can set up our cooling. But the sulfate aerosols have a short residence time in the atmosphere, so we can't really use this mechanism on its own to suggest why the ice cover has been sustained subsequently, and thus why it's only in and around 2005 to 2010 that the mosses of this age are now being exposed back at the surface again as the ice melts. The answer to this that the authors suggest is that what the volcanism actually does is it sets up a significant and critically a self-sustaining positive feedback mechanism linked to the relationship between sea ice and the ocean. And this is the model in detail. So we start off with our volcanic eruption, and that introduces sulfate loading of the atmosphere. That of course induces cooling, and we get an extension of the ice cover. What we're going to have is a situation then over relatively short time where we drop sulfate loading out as a factor, because the effects of it are short-lived, and we should then return back to the same levels of total solar irradiation as we had a few years, or at most a decade or so previously. Now the effects of that then, of course, should be to initiate warming, undo the effects of cooling. The ice cover that had previously extended should effectively retreat, and the system should return to the state that it was in previously. So our mosses that were entombed in, say, 1 decade should be re-exposed within 10 years or so again, not entombed away for the best part of 5 or so centuries. So what we clearly need then, given that this definitely did happen, is something that prevents these effects that we see here. In other words, something that more than compensates for the effects of the increase in total solar irradiance. So what we need is something whereby the effects of the total solar irradiance are more than compensated for by another mechanism in order to sustain that ice over centuries. And that, the authors suggest, is a sea ice ocean feedback mechanism. And this is it in summary. So what happens is that as the ice cover extends, we get increased southward migration and export of sea ice, which has the effect of putting fresh water into the North Atlantic, into subpolar regions. And that freshens these subpolar water masses. It causes a stratification where fresher waters overlie more saline waters, and we impact negatively, we retard open ocean convection. If we do that, if we reduce the convection mechanism, we don't overturn the ocean waters to the same extent, and we inhibit the melting of the sea ice that has begun to develop. And that, of course, then encourages further extension of the ice, further southward export of the sea ice, and the same cycle. Ultimately, of course, the cycle reaches a balance, and then, of course, the system reaches a state whereby it maintains itself rather than continues to develop further until such time as a variable is changed. For example, in the later part of the 20th century, change in climate is sufficient then to induce a retreat of the ice and the exposure of the mosses killed 5 centuries or so previously. So the key point about that is that even though the sulfate loading of the atmosphere is very short term, and its negative effects are actually compensated for by a return to higher values of total solar irradiance, because this feedback mechanism, this positive feedback loop, has become established in the interim period, we maintain the ice cover over the subsequent centuries. Now, there's a couple of other points to take away from this. It's clearly a complex mechanism, and I've put it in for that very reason, to show how one driver stimulates another, even though the effect of the first driver is relatively short term and in fact is undone subsequently via the rise in total solar irradiance. You don't need to drive this model for the subsequent centuries by any fluctuations in total solar irradiance. The other interesting feature about this is the relatively loose definition of little ice age that different authors have used, and the non-correspondence between the specific period of the Maunder minimum and the little ice age in its broadest temporal sense, and it suggests a series of complex, perhaps different factors having different relative importance at different times over the entire period.